Okay guys, so this is the first lesson I'll be filming for you from home since everything has been changing at school, but hopefully this will still be quite useful, particularly for those of you who are going to be going on to study maths as well. So we're going to start off by looking at something that's called numerical methods. Now you've actually looked at numerical methods before. In GCSE you will have done the topic called iteration, which was something that allowed you to find better and better approximations to the solutions of an equation. And I know some of you don't always remember things from GCSE, so we're definitely going to make sure that we revisit this. And we're also going to look at some more powerful methods for approximating these solutions. So there's basically two different things within this topic. There's going to be this one here, which is to do with iterations, and then the second kind of thing that we're going to do is the Newton-Raphson model. I think probably today we're going to get through these first two things that we've got here, okay? So, first of all, why do we even need numerical methods? Well, to find the root of a function, when we talk about the root of a function, it actually means to solve the equation f of x equals 0. So we're trying to say, what are the inputs so that the output of the function is 0? Now, we do this all the time. We always find roots of equations by where something crosses the y-axis, the x-axis. But some of the equations are going to be much harder to find what the exact roots actually are. So for example, this cubic equation that we've got here, if you were to solve this cubic equation, you'd probably just put it into the polynomial equation solver in your calculator. But to find the exact root, it would actually be something that looks as complicated as this. So it's not necessarily going to be the best way of us trying to solve an equation exactly. A numerical method is going to be better. Sometimes there is no algebraic expression at all, so you can't even have it with roots or logs or sine or cos. Like here we have cube roots and fractions. The solution to the equation, the root of the equation x minus cos x equals 0, has no exact solutions that you can express. It's just a number that looks something like this on the graph. So what I've done here is I've taken the graph y equals x minus cos x, and when we talk about the root of the graph, we're talking about where it crosses the x-axis. So this one has no exact solution, but it has a variety of different approaches we can take with some numerical methods, which gives you better solutions to the equation of this, to find this point that we've got here. And we've already seen iteration as one of these methods that you might have to start off with, okay? So the first thing we need to know is about how we prove that a particular solution lies in a given range that they might tell you. So when you have a look at this graph that we've got here, this is f of x, or y equals f of x, and it is of e to the x plus 2x minus 3. So we can see it's some variation on an exponential graph because of this e to the x that we've got here. Now we want to show that it has a root between x equals 0.5, which is going to be somewhere over here, and x equals 0.6, which is somewhere over here. And you can clearly see that there is a root that goes between those two things. Now, our strategy for doing this is what we want to do is we want to substitute in x equals 0.5 and x equals 0.6 into f of x, and we're going to see if we can work out what happens. So first of all, when we do f of 0.5, I'm going to actually substitute 0.5 into the function. So that's e to the 0.5 plus 2 times 0.5 minus 3, and we're going to see what we get. Hopefully this will give us an idea of what we're going to be doing with this topic. So I'm going to put into my calculator e to the 0.5 plus 2 times 0.5 minus 3, and we get the answer minus 0.35127, and that just keeps going. I'm also going to substitute in 0.6, and hopefully we're going to see why this might work in just a second and what it is we're actually trying to do here. So when I substitute 0.6 into this equation, I can actually just go back to my calculator and change those values to 0.6. The answer that we get is 0.02211 blah blah blah. Now if we look at what's happened on the graph here, when we put in a value of 0.5, our graph is actually below the axis. When we put in 0.6, the graph goes above the axis. So we can see that because this value here is negative, and this value that we've got here is positive. And because the thing we're trying to find is where it crosses 0, that must mean that in between these two values, the 0.5 and the 0.6, is where the root must be, because it's going from negative to 0 to positive, and the 0 is the thing that we look for. So what they would look for in the mark scheme for this point is they would then look for you to say something like, whoops, because there is a change in sign and f of x is continuous, and I'll explain what I mean by this in a second. Because there is a change in sign and f of x is continuous, there is a root for f of x between 0.5 and 0.6. And just to reiterate what I mean here, when I say a change in sign, I mean from going from negative to positive. If it's negative over here and it's positive over here, in between those two gaps, it must have crossed the axis. So just the things that they look for in the mark scheme is they always look for finding the function output for the two values, like we did here, and then in the comment they look for you to talk about there being a change in sign, and they also need you to say that the function is continuous. So there's those three things. They need to see the inputs, with it being negative and positive, the comment about the change in sign, and also that the function is continuous. Why, though, is it only true if the function is continuous? Well, if you think about this graph that we had here, continuous means that it just smoothly runs across the page. You can move across the page without taking your pen off it, okay? So I'm actually just write that at the top here. A function is continuous if you can trace it without taking your pen off page. Obviously, this is not a mathematical definition. This is just a way for us to think about what it means for something to be continuous. So the example that we're going to look at here to show why it needs to be continuous is because here it says when f of x is 1 over x, here's our reciprocal graph that we've got here. When you put in -1, you get an answer of -1. But when you put in 1 to the function, you get an answer of 1. So you might say, okay, well, here we go. We've gone from there being a -1 to a 1, so we've got a change in sign. So because there has been a change in sign, we might think that the function has got a root in the range -1 to 1. But clearly, it's not crossing the axis anywhere between -1 and 1. And the reason this is incorrect is because this function here is not continuous. If you tried to trace this without taking your pen off the page, it's not going to be possible to do. So a function is continuous if the line does not jump. Here our line jumps from being -infinity up to +infinity. A root is only guaranteed with a sign change if the function is continuous, as otherwise the line can skip past 0, in this case due to a vertical asymptote. So that's why on that previous page here it's so important that we have to say that f of x is a continuous function. Sometimes it's also careful to see that if you don't have a change in sign, it doesn't always mean that there isn't a root. So for example, here you might put in this particular value and get a negative. You might put in another particular value and get a negative, and you might think, oh, okay, well, because they're both negative, the graph must be something that's like this. There can't be any root that's inside this range that we've got here. But if you imagine, it could be that the range you chose wasn't small enough. So if you think about the graph that it actually is, if you think about this actual graph that you've got here, there is some roots that are actually inside. There could actually be 2 roots in this gap here. It could just be bending up and coming back down again. So you could counteract this by sort of reducing the gap of things that you'd be putting in. So here I've just written that just because there's a change in sign, it doesn't mean that there's no root in that interval. and the sign change method fails to detect a root if there was an even number of roots in that interval. So here you've got two roots that are inside this interval, they're both negative, so that makes you think that there's not a change in sign and that there's no roots, but there could actually have been two that were in there as well. Okay, we'll just finish up this bit by proving a solution to a given accuracy. So this one that we've got here, we've been given some equation that we're going to need to use numerical methods for, and we're going to try and choose a suitable interval to show that this alpha is equal to 2.307 correct to 3 decimal places. So this, you kind of need to think back to a bit about some of the things you might have done at GCSE. We're going to try and find a suitable interval. We're going to find two values that when you put these two values in, if you rounded it, it would go to 2.307 to 3 decimal places. Well, the bottom one of this would be 2.3065. If you rounded that up to 3 decimal places, it's going to go to 2.307. And the top end is going to be 2.3074999999, which we can actually just say is just going to be 2.3075. So if we can substitute these into our g function that we've got here, and if we can show that there is a change in sign, then the root must be between these two things. And if the root is between these two things, then that must mean that the root, when it rounds to 3 decimal places, is 2.307. So let's actually do this. Let's see what happens when we substitute these in. I'm going to put in 2.3065 into the function, which is e to the 2.3065 minus 1 plus 2.3065 minus 6. Okay, next time I won't write out the full substitution, but just for the first time here. So that's e to the 2.3065 minus 1 plus 2.3065 minus 6. We get minus 2.75 times 10 to the minus 4. So it's clearly negative. I'll substitute in my next one, which is 2.3075. And I'm just going to go straight into my calculator with that one and see if I can save myself a bit of time. So I'm just going to change that to a 7.5. And I'll change that to a 7.5 as well. And this time we get 4.419 times 10 to the minus 3, which is greater than 0. So here, there is a change in sign, and g of x is continuous. So alpha is in the range, or in the interval I should say, 2.3065, 2.3075, and hence alpha equals 2.307 to 3 decimal places. Just think again, if you rounded either of these numbers to 3 decimal places, anything inside this range would round to 2.307. Obviously we sometimes say, oh, wouldn't that one round to 2.308? But actually we're really saying here it's 2.307499999, which would round down. So it's basically just the same thing as it being 2.3075. Okay, nearly there for this first bit. So this time it says, using the same axes, sketch the graphs of y equals ln x and y equals 1 over x. Explain how your diagrams show that the function y equals ln x minus 1 over x has only one root. Okay, so first of all, let's do the sketching and see what happens. So I'm going to draw my two sets of axes that I've got here. Now we know that an ln graph looks like this kind of shape. It's that reflection of the exponential graph from the line y equals x. So I'm just going to label that one to begin with. That's my y equals ln x. And then I'm going to draw my 1 over x graph, my reciprocal graph, which we know looks like this and looks like this. Okay, so there's the first part done, where I have sketched the graphs of y equals ln x and 1 over x. And now it's asking you to say why y equals ln x, whoops, crazy pen, so erase this. So it's asking us to say why it has y equals ln x minus 1 over x, only got one root. Well, remember, if something has a root, we're talking about when something is equal to 0. So really what we're saying here is that the root is where we have ln x minus 1 over x equals 0, i.e. when ln x equals 1 over x. Now just have a think to yourself for a second. ln x equals 1 over x. What does this look like when we're thinking about a graph? This is the intersection of y equals ln x and y equals 1 over x. So now we can think about what they've actually asked us. We were saying, when does this have a root? Well, this has a root when these two things are equal to each other, which is the intersection of y equals ln x and 1 over x. And it only has one root. So you can see that because it only crosses in one place. So we should say here, the function only has one root because the graphs only intersect once. Okay, part B, show that the root lies in the interval at 1.7 to 1.8. So we're going to do the same thing as before. We're saying that our f of x is equal to ln x minus 1 over x. So we're going to put in both of those things that we've got. This is for part B of the question. We're going to put in 1.7, which is going to be the ln of 1.7 minus 1 over 1.7. And we're hoping to get a change in sign here. So that's going to be, just on my calculator, ln of 1.7 minus 1 over 1.7, and I've got minus 0.057, and I like just to say to myself that's less than 0. And this time I'm not going to show the substitution, I'm just going to go straight in. So I get ln of 1.8 minus 1 over 1.8. We're hoping for a positive now, and it is positive. We have got 0.03223. which is greater than 0. So remember, you need that concluding statement. There is a change in sign. Whoops. And f of x is continuous. So the root lies in the interval 1.7, 1.8. Part C of the question then says, given that the root of f of x is alpha, show that alpha equals 1.763, correct to 3 decimal places. So we're going to do that same thing that we did before. We're going to think, what would be the upper and lower boundaries of this so that it rounds to 1.763 to 3 decimal places. So this time we're going to try 1.7625, and the other one we're going to try is 1.7635. This one's gone like a 0.5 down, this one's gone like a 0.5 up, and the range of values here are all going to round to 3 decimal places. So I'm just going to go back and change my function again. I'm going to input 1.7625 for these. You can see why they're called numerical methods, because there's an awful lot of calculators being used. That's what it really means. So we've got minus 6.4 times 10 to the minus 4. Notice how it's much closer to 0 than either of these ones are over here, because we're getting much, much closer to the solution. And then we're going to change these as well to 1.7635. So let's just get that, and we're hoping for a positive now. And it's 2.46 ... times 10 to the minus 4. So again, change in sign. continuous function, and so we get alpha equals 1.763, correct to 3 decimal places. Okay, so this should give you enough information to be able to have a go at exercise 10A. If you've got any questions from exercise 10A, let me know and we'll see how it goes, and we'll come back and do some of the other bits in a second.